A main structure's grounding electrode system can indeed serve as the grounding electrode system for a detached structure under specific conditions outlined in the National Electrical Code. It is crucial to understand these requirements to ensure electrical safety and compliance. The primary consideration is that a grounding electrode system, often referred to as a GES, must be properly established at each building or structure. This system provides a low impedance path for fault current to return to the source, facilitating the operation of overcurrent protective devices like circuit breakers or fuses, thereby minimizing the risk of electrical shock and fire. When dealing with detached structures, the code permits the grounding electrode system of the main building to serve as the grounding electrode system for the detached structure, provided certain criteria are met. The key requirement is that there must be a grounding conductor run from the detached structure back to the main structure's grounding electrode system. This grounding conductor is typically run with the supply conductors that feed power to the detached structure. This arrangement creates a continuous and effective grounding path. The size of this grounding conductor must be adequate to handle the potential fault current. The National Electrical Code specifies the minimum size of the grounding conductor based on the size of the ungrounded conductors supplying the detached structure. A grounding electrode system typically consists of one or more grounding electrodes that are bonded together to form a comprehensive grounding network. Common types of grounding electrodes include ground rods, ground plates, metal underground water pipes, and concrete encased electrodes, also known as UFA grounds. Ground rods are commonly used and must meet specific requirements regarding their size, material, and installation depth. Ground plates must also adhere to minimum size and material specifications. Metal underground water pipes, if used as grounding electrodes, must have supplemental grounding electrodes bonded to them to ensure redundancy and reliability. Concrete encased electrodes must be encased within at least 2 inches of concrete that is in direct contact with the earth. The bonding of these various grounding electrodes is critical to create a low impedance path for fault current. Bonding jumpers are used to connect the different grounding electrodes together, as well as to connect the grounding electrode system to the building's grounding busbar or terminal. The size of these bonding jumpers must also comply with the National Electrical Code requirements based on the size of the service entrance conductors. When the main structure's grounding electrode system is used for a detached structure, the grounding conductor that runs between the two structures effectively serves as a bonding jumper, connecting the detached structure's grounding system to the main structure's grounding electrode system. The National Electrical Code provides detailed tables and guidelines for sizing grounding conductors and bonding jumpers to ensure they can safely carry the maximum potential fault current. These tables take into account the ampacity of the supply conductors and the material of the grounding conductors, typically copper or aluminum. Proper installation techniques are also essential for ensuring the effectiveness of the grounding electrode system. Ground rods must be driven to the required depth, and all connections must be made using approved methods and materials. Connections must be mechanically sound and electrically conductive to minimize resistance. The grounding electrode system must also be protected from physical damage. Ground rods, for example, should be located in areas where they are not likely to be damaged by vehicles or equipment. The location of the grounding electrode system should also be accessible for inspection and maintenance. Regular inspections can help identify any potential problems, such as corrosion or loose connections. In addition to the grounding electrode system, it is also important to ensure that all metal parts of the electrical system are properly bonded together. This includes metal conduits, metal enclosures, and metal equipment frames. Bonding these metal parts together creates an equipotential plane, minimizing the potential for voltage differences that could create a shock hazard. The National Electrical Code specifies the requirements for bonding these metal parts together, including the size and type of bonding conductors to be used. These bonding conductors must be securely connected to the metal parts using approved methods and materials. The grounding electrode conductor, which connects the grounding electrode system to the neutral busbar or terminal in the service equipment, is another critical component of the grounding system. The size of the grounding electrode conductor is determined by the size of the service entrance conductors. The grounding electrode conductor must be securely connected to the grounding electrode system and to the neutral busbar or terminal using approved methods and materials. The purpose of the grounding electrode conductor is to provide a low impedance path for fault current to return to the source, facilitating the operation of overcurrent protective devices. In summary, using a main structure's grounding electrode system for a detached structure is permissible under the National Electrical Code, provided that a grounding conductor is run between the two structures and that all applicable requirements for grounding conductors, bonding jumpers, and grounding electrodes are met. Proper installation techniques and regular inspections are essential for ensuring the effectiveness of the grounding system. Always consult the latest edition of the National Electrical Code and local electrical codes for specific requirements and guidance. Grounding electrode systems are essential for protecting people and property from electrical hazards. By understanding the principles and requirements of grounding, you can help ensure a safe and reliable electrical system. The grounding system is not designed to carry current under normal operating conditions. Its primary purpose is to provide a low impedance path for fault current to return to the source, facilitating the operation of overcurrent protective devices. However, the grounding system can also help to reduce electrical noise and improve the performance of sensitive electronic equipment. A well-designed and properly installed grounding system is a critical component of any electrical system. It is important to consult with a qualified electrician to ensure that the grounding system meets all applicable requirements and is properly installed. The National Electrical Code provides comprehensive guidance on grounding and bonding, including detailed tables and examples. By following the code requirements and best practices, you can help ensure a safe and reliable electrical system. Grounding is often confused with bonding, but they are distinct concepts. Grounding refers to the connection of the electrical system to the earth, while bonding refers to the connection of metal parts together to create an equipotential plane. Both grounding and bonding are essential for electrical safety. The grounding electrode system must be installed in accordance with the National Electrical Code and local electrical codes. The code specifies the types of grounding electrodes that are permitted, as well as the requirements for their installation. The grounding electrode system must be accessible for inspection and maintenance. Regular inspections can help identify any potential problems, such as corrosion or loose connections. The grounding electrode system must be protected from physical damage. Ground rods, for example, should be located in areas where they are not likely to be damaged by vehicles or equipment. The grounding electrode system must be properly sized to handle the potential fault current. The size of the grounding electrode conductor is determined by the size of the service entrance conductors. The grounding electrode system must be connected to the neutral busbar or terminal in the service equipment. The grounding electrode system must be connected to all metal parts of the electrical system, including metal conduits, metal enclosures, and metal equipment frames. The grounding electrode system must be connected to the metal water piping system. The grounding electrode system must be connected to the building steel. The grounding electrode system must be connected to any other metal objects that are likely to become energized. The grounding electrode system must be tested periodically to ensure that it is functioning properly. The test should be performed by a qualified electrician. The grounding electrode system must be maintained in good condition. Any damaged or corroded components should be replaced immediately. The grounding electrode system is an essential part of the electrical system. It is important to understand the principles of grounding and to follow the code requirements to ensure a safe and reliable electrical system. The grounding electrode system is not a substitute for overcurrent protection. Overcurrent protection devices such as circuit breakers and fuses are designed to protect the electrical system from overloads and short circuits. The grounding electrode system provides a low impedance path for fault current to return to the source, facilitating the operation of overcurrent protective devices. The grounding electrode system is not a substitute for ground fault circuit interrupters, or GFCIs. GFCIs are designed to protect people from electrical shock. They work by detecting small imbalances in the current flowing through the circuit and tripping the circuit breaker if an imbalance is detected. GFCIs are required in certain locations, such as bathrooms and kitchens, where there is a high risk of electrical shock. The grounding electrode system is not a substitute for surge protection. Surge protection devices are designed to protect electrical equipment from voltage surges, such as those caused by lightning strikes. Surge protection devices are recommended for sensitive electronic equipment. The grounding electrode system is an important part of a comprehensive electrical safety plan. A comprehensive electrical safety plan should include overcurrent protection, ground fault circuit interrupters, surge protection, and a properly installed and maintained grounding electrode system. The grounding electrode system should be inspected regularly by a qualified electrician. The electrician can check the grounding electrode system for any signs of damage or corrosion and can test the system to ensure that it is functioning properly. The electrician can also provide recommendations for improving the grounding electrode system. The grounding electrode system is a critical component of the electrical system. It is important to understand the principles of grounding and to follow the code requirements to ensure a safe and reliable electrical system. Always consult with a qualified electrician for any questions or concerns about the grounding electrode system. The information provided in this narration is for general informational purposes only and does not constitute professional advice. Always consult with a qualified electrician for any specific electrical needs. The National Electrical Code is a complex and constantly evolving document. It is important to stay up to date on the latest code requirements to ensure compliance. The grounding electrode system is just one part of a comprehensive electrical safety plan. It is important to consider all aspects of electrical safety when designing and installing an electrical system. The grounding electrode system is a vital component of electrical safety. A properly installed and maintained grounding electrode system can help protect people and property from electrical hazards. This involves ensuring that the connections are tight and free of corrosion, and that the grounding electrodes are properly installed and maintained. Checking the resistance to ground is another important aspect of grounding system maintenance. High resistance can indicate a problem with the grounding electrode system, such as corrosion or a loose connection. Regular testing can help identify and address these problems before they lead to a safety hazard. In addition to the technical aspects of grounding, it is also important to consider the human element. The electrical safety training is essential for anyone who works with or around electrical equipment. This training should cover the principles of grounding, as well as other important electrical safety topics. By educating workers about electrical hazards and how to avoid them, you can help prevent accidents and injuries. Grounding is a critical aspect of electrical safety that should not be overlooked. By understanding the principles of grounding and following the code requirements, you can help ensure a safe and reliable electrical system. Always consult with a qualified electrician for any questions or concerns about grounding or other electrical safety matters. They have the expertise and knowledge to help you protect yourself, your family, and your property from electrical hazards. This is because the grounding system provides a low impedance path for fault current to return to the source, which helps to trip the overcurrent protection device quickly and effectively. Without a proper grounding system, fault current may take other paths, such as through a person's body, which can result in serious injury or death. The grounding system also helps to reduce electrical noise and interference, which can improve the performance of electronic equipment. By providing a stable reference point for voltage, the grounding system helps to minimize voltage fluctuations and distortions that can affect the operation of sensitive equipment. In addition to protecting people and equipment, the grounding system also helps to prevent fires. Electrical fires are often caused by arcing faults, which occur when current flows through an unintended path due to a breakdown in insulation. A proper grounding system helps to contain these arcing faults and prevent them from spreading, which can reduce the risk of a fire. The grounding system is an essential part of any electrical system, and it is important to ensure that it is properly designed, installed, and maintained. Always consult with a qualified electrician for any questions or concerns about grounding or other electrical safety matters. Grounding is the process of connecting the non-current carrying metal parts of an electrical system to the earth. This provides a low impedance path for fault current to return to the source, which helps to protect people and equipment from electrical shock and fire. The grounding system consists of several components, including the grounding electrode, the grounding electrode conductor, the equipment grounding conductor, and the bonding jumpers. The grounding electrode is a metal rod, plate, or other object that is buried in the earth. It provides a direct connection to the earth and helps to dissipate fault current. The grounding electrode conductor connects the grounding electrode to the neutral busbar in the service equipment. It provides a path for fault current to flow from the electrical system to the grounding electrode. The equipment grounding conductor connects the non-current carrying metal parts of the electrical system to the grounding electrode conductor. It provides a path for fault current to flow from the equipment to the grounding electrode. Bonding jumpers are used to connect different metal parts of the electrical system together. This helps to create an equipotential plane, which minimizes the voltage difference between different metal parts and reduces the risk of electrical shock.